G'day viewers. In this episode we consider the physical meaning of the particle radii estimates generated by the particle-antiparticle pair representation developed by Schipper. The concept of particle size is ambiguous because subatomic particles do not have a solid surface. Hence, what does particle size actually mean when scientists claim that a subatomic particle possesses a certain radius? Well, if a calculation of particle radius is accompanied by descriptions such as root mean squared charge radius or mean squared charge radius, then the physical meaning of particle size is communicated clearly. However, in the case of the Schipper particle radii derivations, no such clarity was issued in the results. Thus, one may legitimately ask the question, what do the Schipper particle radii results physically mean? To answer this question, we align the Papa construct with the electrogravimagnetic construct, specifically with respect to the harmonic representation of subatomic particles. En route, we achieve the following significant outcomes. Number one, we convert the particle radii estimates from the Papa construct into the zero-point field equilibrium radii estimates congruent with the EGM construct. In other words, we derive the radius in which a subatomic particle exists in energetic equilibrium with the space-time manifold surrounding itself. That is, in energetic equilibrium with the zero-point field surrounding itself. This action yields the physical meaning of particle radii, which we have been seeking from the Papa construct. Number two, we establish the framework to build a harmonic representation of subatomic particles based upon the Papa construct, instead of the EGM construct. Thus, by simply and literally filling in the harmonic blanks, we predict the potential existence of new particles. This does not mean that the predicted particles are stable. That is, some or all of the predicted particles might denote transient energy states only. There is no way to tell. Our results imply the potential existence of 1 additional baryon, 2 additional mesons, and up to 39 additional bosons. Okay, let's get into it. Let's begin our journey by identifying where the Schipper research article can be found, as we did in episodes 98, 99 and 100. Now that you know where to find the primary artifacts, let's expand Schipper's particle radii model to include harmonic solutions. If you have not already watched episodes 98, 99 and 100, please pause this video presentation and watch the previous episodes before proceeding. Moreover, we strongly encourage viewers to review the Staughty 2007 research article listed and the periodic table of harmonic solutions video presentation appearing on our channel. Please refer to episode 8. Well, assuming that you have followed my instructions, let's review Schipper's results from episode 98. Schipper's results contain 3 columns of quantitative information, that is, his calculated radii, the radii from a literature review, and the percentage deviation between them. As you can see, we have boxed the column containing the radii values from Schipper's literature review. Why have we done this? Well, we have done this because no direct connection exists between Schipper's calculated radii values and the electromagnetically associated radii values obtained from his literature review. Although Schipper's results appear impressive upon first exposure, closer scrutiny reveals that there is nothing in Schipper's particle radii derivation process which associates the form of radii appearing in the nomenclature with his calculated radii. In other words, as presented, Schipper's calculated particle radii appear to be incomplete or unfinished, as they do not infer any like-for-like association with the literature review results. Schipper does not reconcile the physical meaning of his radii results against charge radii, magnetic radii, electric radii, or simply radii. In the bottom right-hand corner of the screen, the Staughty particle radii equations are presented, which do not contain any electric or magnetic terms. The fact that these equations do not contain such terms is extremely important, as you will soon see, so please keep this in mind. Let's now do a side-by-side comparison of the Schipper versus Staughty results. Staughty's particle radii results present 4 significant features against Schipper's formulation, as follows. Number 1. Staughty's results match Schipper's results precisely. By inspection, we can see that any differences between them are trivial and may be discarded. Number 2. Staughty's particle radii equations do not contain any electric or magnetic terms, as discussed on the previous slide. Number 3. Staughty's particle radii equations do not contain a spin angular momentum term. This is extremely important because it invalidates Schipper's propositions regarding particle spin and helicity. Number 4.
Storti's particle radii equations do not contain a mass moment of inertia term. This means that all the baryons, mesons and bosons presented may be modelled as point particles, where the mass moment of inertia configuration coefficient I sub x equals 0. As appears on the right-hand side of Table 2, we have averaged the radii values stated in Schipper's research article. Please refer to the previous slide. Moreover, we have concatenated the particle radii description obtained from Schipper's literature review. By executing these changes, we are able to succinctly emphasise the lack of like-for-like association between Schipper's calculated particle radii and his literature review results. The process for establishing particle-antiparticle pair representation harmonics is not difficult nor complicated. That is, it can be executed in 4 simple steps. However, to the uninitiated observer, the process may appear to be complex. Hence, we shall walk through the process for the sigma and z particles. Having said this, we recommend that you download, review and digest the literature referenced on screen. Moreover, we recommend that you review episode 8. In order to avoid this video presentation requiring an hour-long investment of your time and repetition of existing information. At this juncture, it would be wise to pause this video presentation and execute the tasks we have suggested. You can come back to this afterwards. Appearing at the top right-hand corner of the frame, you can see the electrogravimagnetic harmonic and zero-point field equilibrium radius equations. These equations are at the centre of the particle harmonics derivation process we shall execute. If you are interested in understanding their origin, then you'll need to undertake the homework we have suggested. In fact, it would be prudent to watch our entire EGM playlist. Within the red boxes, you can see various labels, such as literature, average particle radii, EGM harmonic, papaharmonic, and papaharmonic radii. The literature labels refer to the numerical estimates or experimental values by third parties quoted by Schipper in his research article. The average particle radii labels refer to the data contained in each set. The EGM harmonic labels refer to the output of the EGM harmonic equation appearing at the top right-hand corner of the frame. The papaharmonic labels refer to a transformation of the EGM harmonic result. The papaharmonic radii labels refer to radii estimates at the end of the particle harmonic derivation process, that is, the output we are seeking to derive. Now that we have described the labels inside the red boxes, let's walk through the derivation in a stepwise manner by following the process arrows. Step 1. Determine the average particle radii. Step 2. Compute the EGM harmonic. Step 3. Transform the EGM harmonic into the papaharmonic. Step 4. Compute the papaharmonic radii utilising the zero-point field equilibrium radius equation. It is important to understand that the papaharmonic radii represents the zero-point field equilibrium radii, which is a quantized property. In other words, the papaharmonic radii has been quantized. So, now that the derivation process is complete, what have we achieved? Well, we have achieved a couple of important things. Number 1, we have converted the point particle estimate for radius via the Papa construct into a zero-point field equilibrium radius estimate congruent with the EGM construct. In other words, we have derived the radius in which a subatomic particle exists in energetic equilibrium with the space-time manifold surrounding itself, that is, in energetic equilibrium with the zero-point field surrounding itself. Number 2, we have established the framework to build a harmonic representation of subatomic particles based upon the Papa construct instead of the EGM construct. Okay, let's now look at some omega, delta and lambda particles. The derivation process for omega, delta and lambda particles is identical to the sigma and z particles we just explored. However, in these examples, we shall focus a bit more attention on the harmonic transformation step. Transforming the electrogravimagnetic harmonic to the particle-antiparticle pair representation harmonic is an intuitive step. The value associated with executing this step becomes apparent across a population of particles, which we shall see going forward. Okay, let's now look at some pionic and bosonic particles. Once again, the particle-antiparticle pair representation harmonic derivation process for pions and bosons is identical to all other particles. In the case of bosons, Schipper's radii estimates are virtually identical to our electrogravimagnetic radii estimates, so no discussion is required because identical harmonics are generated. Okay, let's now analyse our results in a tabulated format. When presented in this format, our results communicate some significant conclusions. Let's start by walking through the column architecture. Columns 1 and 2 are self-explanatory. Column 3 contains particle radii estimates as calculated by Storti in episode 98, utilising a variant of the Shipper method. Column 4 contains Papa harmonic values. The number 1 appearing in the column denotes the fundamental harmonic. It also represents the proton harmonic, that is, the proton is utilised as the harmonic reference particle within the EGM construct. Please refer to episode 8 for more information. The fractional values of 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8 and 1/10 denote subharmonics. The integer values of 99, 109 and 141 denote higher harmonics. Column 5 contains radii estimates generated by the harmonic method we have outlined. We have converted the point particle estimate for radius via the Papa construct into a 0-point field equilibrium radius estimate congruent with the EGM construct. In other words, we have derived the radius in which a subatomic particle exists in energetic equilibrium with the space-time manifold surrounding itself, that is, in energetic equilibrium with the 0-point field surrounding itself. Column 6 is particularly important because it contains the particle radii estimate deviation between columns 3 and 5. What we can see is that across the population of particles presented, an average deviation of less than 3.6% exists between particle radii estimates. Column 6 provides clear mathematical evidence that the harmonic representation of subatomic particles we have developed utilising the Papa construct has been conceptually validated. Okay, let's now look at predicting the existence of some new particles utilising our harmonic methodology. By simply and literally filling in the harmonic blanks, we are able to predict the potential existence of new particles. This does not mean that the predicted particles are stable. That is, some or all of the predicted particles might denote transient energy states only. There is no way to tell. Our results imply the potential existence of 1 additional baryon, 2 additional mesons and 39 additional bosons. One of our meson particle predictions appears improbable, as emphasised. However, it should be noted that despite this improbability, the average harmonic deviation value remains relatively low, that is, at less than 7.2%. This implies that the overall harmonic solution we have developed is quite robust, and new particle predictions should not be discarded without due consideration. Okay, let's now summarise what we have learned. On our journey, we have aligned the particle-antiparticle pair representation developed by Shipper with the electrogravimagnetic construct developed by Storti and Desiato, specifically with their harmonic representation of subatomic particles. En route, we have achieved 5 significant outcomes. Number 1, we have converted the point particle estimate for radius via the Papa construct into a 0-point field equilibrium radius estimate congruent with the EGM construct. In other words, we have derived the radius in which a subatomic particle exists in energetic equilibrium with the space-time manifold surrounding itself, that is, in energetic equilibrium with the 0-point field surrounding itself. Number 2, we have established the framework to build a harmonic representation of subatomic particles based upon the Papa construct instead of the EGM construct. Number 3, by simply and literally filling in the harmonic blanks, we were able to predict the potential existence of new particles. This does not mean that the predicted particles are stable, that is, some or all of the predicted particles might denote transient energy states only. There is no way to tell. Number 4, our results imply the potential existence of 1 additional baryon, 2 additional mesons and 39 additional bosons. Number 5, one of our meson particle predictions appears improbable. However, it should be noted that despite this improbability, the average harmonic deviation value remains relatively low, that is, at less than 7.2%. This implies that the overall harmonic solution we have developed is quite robust, and new particle predictions should not be discarded without due consideration.